Hello, and welcome to this webinar presented by the IET Cambridge Network. We represent members in the Cambridgeshire area, but we're very pleased to welcome folks from around the UK and indeed globally. My name is Phil Zengast. I'll be your host tonight. I'm the chair of the local network. Before we come to the event, we will just cover some housekeeping points. We'll leave questions to the end of the event. So if you've got something you want to ask, please use the Q&A button, which you'll find at the bottom of the screen in the Zoom control panel. That's the Q&A button, please. We'll endeavour to answer all your questions tonight, but if we don't, our speaker has offered to answer those offline, and we will post the answers on our IET Cambridge website. We'll be recording the event tonight, and that'll also be available on our YouTube channel, which you can find by searching YouTube for IET Cambridge. Now, I'll just mention a survey that the IET is running this year on the subject of diversity and inclusion, and I will put some details on that on the chat panel during the event tonight. And finally, I will mention that our next event is on the 20th of May, and that'll be on the subject of the Hydroflex hydrogen-powered train project. Now, on to tonight's event, and I'm very pleased to welcome our speaker, Marco Ghibaudi. Marco is Vice President of Engineering at Riverlane here in Cambridge. He's an FPGA expert and has a PhD in innovative technologies. And during his PhD, he worked on the electronics, the back-end electronics for the Atlas experiment at CERN. And he's also developed prototypes for use in the IoT, communications and automotive field. And over the last 5 years, he's worked for a number of companies in the field of system on chip and consumer electronics. So without further ado, I will hand you over to Marco Ghibaudi. Marco.
Hi Phil, thanks. I'll start sharing in a second. Okay, so let me move to the presentation mode. Okay. Hi everyone, thanks for being hopefully being here. I think this will be 45 minutes of me trying to explain something really complex that I recently started working on, that is quantum computing. I joined Riverlane 1 year and a bit ago, so I'm still on the quantum side. I still have things that will need that might require my colleagues to jump in and help me, but I'll do my best to take all the questions and come back more prepared if you have something that I can't tackle today, and rely an answer to you. Okay, so what I'm trying to do today is to first of all explain why we believe that quantum computers are important and why we need them. And the next step will be to explain why what's inside a quantum computer in a sort of general fashion. And then I'll move into explaining with this example of the spherical cow what's really why we think is an engineering problem and not just a physicist problem. And then I'll do a bit of like explanation of what Riverlane is doing and why we think we have something uncommon and interesting for everyone. So actually, yeah, I managed to. Okay, excellent. So Schroedinger. Let's start with why. On top of explaining with Schroedinger, I think most people are familiar with. I just want to jump in a second on the cat and why the title is the Python in the box. So all the quantum physics has been the base for quantum computing. It has been kind of discovered already beginning of the 19th century with Einstein and Heisenberg and Schrödinger, but the real application are starting now. The main reason is technology, and the theory has not in quantum science, in quantum physics hasn't moved much in that sense. What has changed is obviously our understanding of how it works in practice and how to recreate it. I want to use an example to just explain what's the difference between a classical computer and a quantum computer before I jump in details. I think my first feeling is that classical computing is you can see it as a supercar, a nice Bugatti that does everything. You can park a Bugatti in a supermarket if you want to. You can go in almost any kind of terrain. A quantum computer is a completely different kind of computational unit. Is kind of a super speed car that can't park, doesn't have any steering. Brakes are a parachute, but it can do 1,000 kilometers per hour max speed. So completely different application, and we don't think that quantum computers will replace classical computers. What we believe is that there will be an ecosystem of applications that use both quantum and classical, and the quantum will be basically an accelerator, what is called a quantum accelerator. Now, why another point that is normally in the media and is worth touching is there is lots of, I read something today as well, lots of rumor about quantum computers making cryptography outdated, and you might be familiar with Shor algorithm. This is something that we believe is obviously important, but is a kind of is the tip of the iceberg of what quantum computers can do. Is the tip of the iceberg in two senses. One, in terms of what speed up the quantum computer can give you. So Shor is an example of the maximum speed up that you can get from a quantum computer. But it is a tip of the iceberg in terms of the amount of application that will benefit from this algorithm. We were talking about factorization of large prime numbers. That is not something commonly used in other fields. We believe, the quantum community believes, that there is more interest in the bottom of this triangle with the optimization and algorithm that are trying to tackle. They provide a smaller speed up, but they tackle a larger set of problems that are like daily problems. And these problems I'll focus on chemistry and pharmaceutical, but they span across finance, transports, technology in general, and as I was saying, chemistry and pharmaceutical. The reason why this is just to give the entity of if we look at the entity of the speed up that we can get. If we look at the top of this of the pyramid that I showed you before, these are the numbers that we're talking about. So if I want, I can have a speed up that is moving from the pink row, so the top one with the classical implementation, to something that will take basically the age of the universe, to something executed on a quantum computer that in the future will take 24 minutes. Again, this is a specific, really niche problem, like the prime number factorization. But there are problems that have a smaller speed up in the order of, instead of being a conversion of exponential into polynomial, they provide a factor of 10 or a factor of 100 reduction that makes quite a lot of difference. There was a nice survey and work from Microsoft that span across different fields, in which they try to find problems that will impact most the society in terms of quantum computers. And there are 4 or 5 in that link. And my favorite one is this one. It's called nitrogen fixation. So the claim of the community that has not been proved yet is that quantum computers will help us with fertilizer. Fertilizer might sound dull, but is with the production of fertilizer is taking about 2% of the global energy resources to be made. And the funny thing is that there are tiny prokaryotes bacteria in the soil that they can do that with a much higher efficiency and requiring much less power. How they do that, we don't really know. We have, obviously, we know enough to understand the process, but we don't know enough to recreate it. So we have a process that was invented at the beginning of the 19th century that has not been optimized, and is the one that is taking 2% of the global power. If we were to manage and understand how the prokaryotes do this conversion, we could reduce this utility bill by a lot. Problem is that this is not something that we can simulate. The resources that we have, even cluster of servers and massive farms, are not. They really struggle when we reach the internal of the enzyme that is responsible for this, and they do that because it's basically a quantum process that needs to be simulated with a quantum simulator. A quantum simulator can run on classical resources, but the best way to run a quantum simulator is via quantum machines, via quantum computers. Now, important probably to, again, is one of those myth busters, explain where we are today. So we are in the yellow proof of concept era. We are slowly moving in towards the semi-usable era that is called NISQ, in which there are qubits. The systems are getting larger, but they are far from being perfect. And the applications that can use them are mainly chemical, pharmaceutical, and physics. This is because the algorithms that we need are more robust to errors, and they can tolerate imperfections in the qubit. When we talk about Shor or cryptography, we will need to be on the blue side of things. And in that case, we are talking about 1 million of qubits and the capability of running basically any quantum problem you want on the quantum machines. Now, these numbers are, if you see, we want to be in the blue ballpark. And these are the numbers that companies, like probably the 2 biggest companies around at the moment, IBM and IonQ, are quoting from the technologies. So if you see, there is a clear doubling or acceleration that is driven by new investments, new technologies, more effort. And we believe that, and IBM and IonQ believe that we will start having something that can be usable for solving some of pharmaceutical or chemistry problems in the next 5 to 10 years. Now, what I mean with chemistry and pharmaceutical problem, I think this was a bit puzzling for me at the beginning. So this slide is, I think this is an enzyme again. And what happens here is that we can simulate classically everything that is grayed out, like kind of the frame around the image. But we care about the really tiny dark green square at the center of the image, because that's it's called the interaction area, the interaction zone of the enzyme, and this is where the interesting things happen. If we simulate that part classically, we get the wrong drugs. We get something that we need, that might fail on clinical trials. If we understand better the rotation of the atoms, the energy, all the information that are quantistic, we can make better drugs. We can make better materials. We can improve all we got so far. And to do that, we need to mix and match, as I was saying at the beginning, all the gray part with classical running on classical resources, and the dark green one on quantum resources. So now we hopefully all know what's a classical computer. Now, what's a quantum computer is one of those things that was a bit shocking to me at the beginning. So quantum computing is basically a massive room, half a building. Is like what was back in the days a supercomputer, like a Cray, or and why? Because there is the quantum part of the system has special properties. So I have 3 examples here. So there are real examples. 1 is in Cambridge, and 2 are Oxford and Sussex. And so we have 3 different. There are mainly 4 or 5 types of technologies. that allows you to implement quantum systems. They are completely different in terms of technology and engineering. The one on top operates at in a vacuum chamber and is operating a low temperature, like kelvins, with electronics that is borrowed from telecommunications. The superconducting is operating at millikelvins. So all the pillar is basically it's called a dilution fridge. Is a way to via liquid nitrogens and combination of lasers and other technologies to bring your material inside the tiny box in the center to 10 millikelvin. Optical are yet another different way to generate optical quantum computers use a different way to generate qubits. All of them, they behave in different way, but they reach the target of defining all these properties that I'll clarify quickly. So we have the same, hopefully we have the same language. So each of these technology implements what's called a gate set. You can see it if you borrow from classical electronics. Basically, is the building blocks that you have, is the AND gate, the NOR gate, etc. They do have similar names. Obviously, they implement different things, but they are the set of your Lego bricks that you can use to build your circuit. Measurement is a concept that is a bit different from classical. So measurement is an active process that understands move away from the quantum side and gives you a classical number. So I have a slide on what I mean with quantum and classical representation, but is basically making it usable by classical logic, for classical logic. A circuit is a similar concept to what you have in electronics, in standard electronics, is a sequence of these building blocks. It looks like a music chart, so there are inputs and outputs, and it goes with the time. Coherence time is basically the amount of time that you can keep a quantum computer usable without doing any refresh. Refresh is a destructive operation that basically makes you start again. So the coherence time is the amount of time that you have to do your computation before you need to pause, take some intermediate results, and continue. There are different ways to define this gate set and these building blocks, but they mainly are one terminal or two terminal blocks. So you can, if you follow the electronics convention, or one input to inputs blocks, and they have different properties and they are used in different ways. The fidelity is the error rate, one would say, the capability of running what you ask for without errors. Problem is that we are in quantum land, so there is the uncertainty principle that comes into play. So we will never get something perfect. So we don't get something that always works. There is always a probability that something will go wrong. Now, this is the representation I was talking about. So if you look at the sphere on the left, it's called block sphere, and that represents the 0 and 1 are what you will imagine as a 0 and a 1 in classical bits. But with quantum computers, you can move in this sphere and generate something that is on the surface of it. So you're basically saying, instead, I still use one element to store my information, but now instead of having two values, I have an infinite number of values that are the rotation, and can be expressed by the rotation and the two angles that are describe the sphere. How do we represent that? Different ways. So if I start with that sphere and I want to change it, I have a matrix representation that tells me that this is two inputs transformation that takes input one and swaps, perform a knot on the second input depending on the value of the first one. Is represented by the cross and the black dot. Other inputs are, you can have a matrix that is a 2 by 2, and that's like a one, basically is one input, one output is one terminal, and this will be just a rotation applied to one single qubit. Now, just to kind of try to connect all the dots here, why do we care? How does it relate to my real problem? So I have this example that is the one we are familiar with. So let's say that I want to analyze the property of a molecule. What I do is I start with the Hamiltonian that represents the molecule. That will tell me what is the dynamics of the system, how it's going to evolve. Now, this is normally something that has an exponential with a really complex matrix that is not computable. The evolution is basically we can't compute the integral, we can't find solve the differential equations around it. We can approximate in classical terms, but the alternative is we can basically break that problem into a set of gates and circuit. So I make that exponentiation the product of multiple circuits and blocks of circuits, and when I measure it at the end, that tells me the result of that Hamiltonian. What's the evolution of the system? I can iterate. In this case, is an iterative process, and I can find out of the solutions. I can find the minimum level, the minimum energy for that specific molecule, for that specific atom. I can use this information, as I said at the beginning, to drive my drug discovery efforts. How does he? When I mentioned the music chart, so this is what I meant with music chart. So this is an example of trying to compute the ground state, so the minimum energy of a hydrogen molecule. I took it from IBM. Is basically we have 4 qubits, Q0 to Q3, and we apply all this different set of operations that give us different values. Everything that is moving until the end is in the quantum domain. We will do measurements at the end that will bring back 4 classical bits that we're going to use to generate some of the numbers that are the digits of the energy of the system. And this is because I broke the Hamiltonian in a way that I can get some of the metrics that I want. Again, why we care? We care because we are not far from having something interesting on quantum computers. As I was saying, we don't really need. We believe that for some aspects, some computation, we don't really need ultra precise computations yet. So with that caveat, we know that we can start compute some complex the properties of some complex materials, atoms, and molecules with just increasing number of qubits that we use. Now, that was what I called the spherical cow, so a lovely approximation of things. Reality is a bit more complex. So when you see there is everything in this picture as there are 4, 5 colors. The colors, they match the images. So we do have loads of electronics involved. We have CPUs in orange. We have large FPGAs. We have fast FPGAs in dark orange. We have ADCs, DACs, and we have lots of. We need all these blocks to operate and work in combination with really strict timing and in a fully distributed way. In some systems, we might have the FPGA layer, for example, composed of 100 or more FPGAs all talking together to create this 100 or 200 qubits state. Top of that, when we dig really deep into and this is probably interesting for microelectronics and RF engineers, so when all these, the superconducting and the ion traps that are the 2 main type of qubits, they require, they operate in radio frequency regimes. So they are about 5 and let's say above 2 gigahertz and below 10 gigahertz, depending on the implementation. And they need, and they operate, on top of that, they operate in ultra cold environments. Really interesting problems like how do I share my RF signals across the chip? How do I design this chip in these new materials, superconducting materials? What kind of simulations, electrical, electronic simulation I can run on them? And to make things even more complex, for example, for ion traps, we have to use CCD cameras to understand what's the status of a qubit. So there are ways to understand if my measurement, to understand if after measurement I am in what's called in a cat 0 or cat 1 state. So if my system has moved to the top of the block sphere or to the bottom, and I need cameras, I need some sort of fast image processing. I need what this image is showing is called shuttling, is a way to move atoms inside a chip inside a PCB by playing with magnetic fields and electrical fields in a sensible way. And this is I think that they're really exciting for microelectronics. Now, if I look at the full execution flow that I find particularly charming, there are even more layers. So we have languages that define the circuit that I want to run. They define the problem I want to solve, like the one on the snippet of code on the right hand side. And I might have this in my editor, Jupyter Notebook, and send it across the ocean to IonQ or to other companies, and they will have local servers, they will have backends, they will have user interfaces, and they will convert it to this kind of music chart representation of the circuit. Then they will compile it to because their hardware is different from a standard representation that you've seen, and they have specificity that they want to leverage. Convert it into a sequence of software and FPGA control, and they will drive the analog components, lasers, radio frequency generators, and cameras, and etc. They might need to do radar style post-processing of the measurements they make to actually understand the status of the qubit. And they will have to do crazy thermal compensations for when something moves from a normal PC sitting in the lab to and from the quantum computer at 10 millikelvin. Final result is at the bottom of the stack. This is the chip that then became after the Google one. They want to control, want to generate signals at this full page is about 300 nanoseconds. So they want to be able to generate this kind of control, and they want all the Zs to be aligned, for example, for cross 1, that is qubit 1, and cross 2, that is qubit 2. And this is not the end of it. So technically wise, there is we could stop there if we were happy with errors. But now we want to move into the future of quantum computers, and we need to fix errors. There is a similar field to error correction that we have in classical computing. It's called quantum error correction. It is more convoluted and complex than the classical one. And that's because the quantum computers have properties that don't allow simplification that we do in classical error correction. This requires really complex solutions like the union find decoder that Microsoft is working on, and to actually understand where the error happened, how the error can be fixed, and produce a solution within the time scale of the 300 nanosecond, microseconds, or few milliseconds. Now, this was a hopefully not rushed view of how is the full ecosystem now. And some of the things obviously Riverlane, we are a software company, so we are more versed on the software side of things. But I hope I did give you an interesting overview of the full stack of quantum computers. And now, what we believe is important. We believe that with this noisy intermediate scale quantum computing, so this era of quantum computers that are okay, but they're not perfect, they're not good enough for most of the applications, we can and we should help the technology, the quantum technology, be in a position like it happened for classical semiconductors. So we want a Moore's law that brings benefit to the hardware, revenues to the hardware lab, creates software, creates applications, it creates an ecosystem, and then will accelerate the development. And we're working in a few different fields. We have worked on a way to, I would say, write once, run everywhere approach. We have focused on improving what is possible with a small number of qubits, and we have finally touched on how this complex stack of classical and FPGA, CPU and FPGAs can be configured from a user perspective, from a physicist perspective. For the write once, run many, we work with all the startups in the UK, quantum startups, and we with NPL, the National Physics Lab, and DARM, and we're trying to standardize the way you talk to quantum computer. All these companies, they have amazing technology, and they are completely different. They have a special type of qubit. They use different physics, but from an application developer, it should be possible to write your application and run on both of them, on 4 of them or 5 of them, and then get the results and decide the next day to run on the other one. So we have done, we think we are at month 12 on this process. We're working in this large collaboration. We are running demos on the systems. We are collecting feedbacks, ideas, and we are trying to create a standard to cover for that. There are lots of standardization efforts ongoing in quantum computing. This is probably the biggest in the UK, I think potentially the only one in the UK. And the interesting bit is we work with 5 quantum labs. There are 35, 34, 35, 36, depends how you count them, in the planet. So we have quite a large data set, base set. We find that developers want to, and each level, any level of the stack, developers want to get a way to control more the system. And because now we are familiar with programming CPUs, we are familiar with writing FPGA code, we have all this, and we need really quantum computers to be effective sooner than later to kickstart this process. And we are working on, again, as the second element, we are working on squeezing the qubits. So with this, we mean we want to get something, and we are not the only one, Honeywell, and I think IBM has been working recently on this as well. We're trying to develop new ways to use the existing qubits, take what's like all the textbook, the Shor or other algorithms, and try to make them more tuned to the hardware that we need. As I was saying, this comes as a optimization at all the layers. If you think about like optimizing a server, for example, uptime and downtime is down to how the CPUs are talking, how memory, and this is just the same problem to a larger scale. We have developed our Delta Flow framework for that, and our goal is to allow this, what we call the levels. So we want to allow users to the possibility of writing code that is quantum code that operates at really fast speed if they want to, or just have a kind of batch execution. and get the benefit of a simpler and interface and programming model. We have done some calculation, like this is best case calculations, in which we show that if you were to use, if you give the user the power to optimize things and use the FPGA logic, the ASIC logic, the low-level control, as we call, some applications will benefit massively. So this again is the best case scenario in terms of speed up, but we believe at by 20 is possible in terms of acceleration. One thing that I was particularly scared at the beginning, I'm an FPGA guy. I've done quite a bit of work before on consumer electronics, and when I joined the company, I was particularly scared of how do you actually program these monsters, how do you work with them? And I was pleased to understand that physicists are always writing Python, and this is what they want. So when I joined, there was this initial effort on what we call Delta Flow. That is a flow, is our framework that lets you write code for this heterogeneous stack, for this heterogeneous type of system, and treat each computational unit in a way that makes easier exchange of data, the verification, and all the things that can block your development. We treat any problem as a graph, and this is a problem this is an experiment that physicists normally do, and we are running on quantum computers. It's just a way of understanding that basically the quantum machine is in a quantum state. It's called Rabi oscillation or Rabi flop. And we have designed it in a way that instead of running in a super slow fashion from your PC, from the server PC of the lab, is executed on the low-level control stack of the FPGA and is returning a much faster speed the solution. So this means better utilization for the lab, faster results for you. We believe also that, as I was saying, you have 500 FPGAs, all of them want to be the boss, and then we are moving away from kind of a centralized control system in which you have some big CPU driving and everything else listening. We are designing a system that is distributed and can tolerate faults and can tolerate different units talking at the same time. Now, what's next? I would say we believe that there will be, well, democratization of things. So the cloud will become quite important. So already companies are giving access to limited number of qubits via the cloud, and this is going to improve. What you will want to do as a developer in the future, you will want to, because a quantum machine is an accelerator, you will want to have GPUs and TPUs and other computational units side to side, and this will give us what we believe combined with quantum machines will give us, quantum computers will give us a lovely factor of 10 reduction or factor of 5 reduction on the total execution time of your problem. So I think the final message in this slide is that, and that's something I'm particularly passionate about, we don't know which technology is going to win. There are obviously even IBM and Google, they are using different implementations. IonQ is using another one, Rigetti, different one. They all have really strong and really important properties, and they achieve really outstanding results, but they have some shortcomings that might remain. So we believe that there will be this ecosystem that will remain heterogeneous in terms of technologies, and that some new technologies might actually appear in the future. To do that, to cover for that, we are trying to give this framework that is open, this hardware abstraction layer that defines a common API of calls to the quantum computer, and a way to optimize via our quantum science team the algorithms that are running on the machine. Obviously, everything needs, we believe that everything needs to come in this specific case from the top to the bottom and vice versa. because we need application developers to tell us what we need, and we need to tell application developers what they can achieve and what they have. As I was saying, we are working with I would say the best companies I work with, and they are all UK based. And yeah, we are looking for really good people, and I'm always trying to get matching talents to the ones we have already in the company. So please have a look at our website if you like this talk. Phil, I'll pass it back to you. I'm just trying to stop sharing. Sorry, my pointer is playing fun. Sorry.
Okay, Marco.
Sorry,
thank you for that introduction, I think, to the field of quantum computing and what you're doing with Riverlane. I suspect you've only just scratched the surface of what you could have covered, but we've got lots of questions now, so I'll hand over to David Blake to work through those. Thank you.
Okay, thank you, Phil, and thank you, Marco, for a very interesting talk. It's not my area of expertise, so please bear with me if some of the questions I ask are not quite appropriate. We've got quite a few questions starting. I also have some my sort of self that I'd like to ask. But first of all, one question here is, what is the semi-empirical method? You only talk about the classical and quantum methods.
Okay, so this will be touching, I think, the area that will normally need my colleagues to help me with. I'll do my best, and I can relay the question and try to come back with the best answer. And my understanding is that we have a pure, we can try to compute in a pure classical fashion using classical computation. What I presented was a mix of classical and quantum. And you can, in chemistry, you can tolerate, you can find approximations that are obviously give you less precise results. They're faster, and they can be augmented with measurements, real measurements, etc. I think I'll stop here on that first part of the question before I say something that is. But I'll be happy to ask my colleagues how would they qualify the difference between a pure classical or a pure quantum and a semi-empirical method for that.
Well, we will download the questions and we'll sort of publish them on our website.
Super, thank you.
Well, there's a second part of the question is, do you think quantum method is better than the classical method?
So if we ignoring the quantum computation part and just looking at the method itself, the properties, you should get chemical accuracy, better chemical accuracy on the quantum method. I'm not familiar with any case in which the classical will give you better results. There is obviously the loads of scenarios in which quantum properties are of no importance to you because the molecule is, the properties you're looking at are macroscopic, or and in that case you will just be fine with the classical, and you will just spend more energy and time with the quantum approach.
Okay. In classical electronics, a gate is built out of transistors. What are quantum gates built from?
Well, this is really nice. Depends on the technology. So I'll give you an answer for the two promising or the two most advanced ones that are superconducting and the ion traps. I start with ion traps. So in ion traps, you basically have ions. So you have a tank full of gas, special gas that gets ionized, and then you load this device with a given number of ions, and you do that via lasers and via keeping a ultra vacuum system. Then these ions behave in a quantum way when you put them near. You control them via lasers again, and you move them using radio frequency and magnetic fields. Everything controlled by, I would say, off-the-shelf electronics, but with like standard signal generators, with like standard lasers, and nothing ultra complex in that sense. Superconducting a bit different. So in that case is what is called a macroscopic atom. So you create something that looks like an atom, but it's not, and is really is basically classical electronics. So you have in a superconducting chip, you have the concept of capacitance, but you have few differences because you're operating at superconducting temperature and superconducting materials. One of that is called the Josephson junction that behaves as a special inductance, and you build a qubit using, you kind of create an harmonic oscillator using this capacitance and this inductance in a way that you can't do at room temperature with a normal electronic. When you have it, you can again use radio frequency and lasers to control it and create the quantum gates out of it. Okay, thank you.
Question that you might be able to answer quickly: how many qubits are in a bit? Or even
how many qubits are in a bit? So how to difficult to, so I would say if you want to express all the possibility of 32 bits in some, obviously in some configuration, you will need gigabyte of memories. So you will need 2 to the power of 32. There are caveats, but we are talking that the information that you can store in a qubit because of the block sphere and this superposition and the capability of this of the information of being stored in not just in 2 ways, but in multiple ways is much larger. There are limitations on what you can on the error, etc., but we are talking like order of magnitudes more and exponentially more.
Okay. Are you working with the Sydney Quantum Academy?
Not that I'm familiar with. It might be something that not that I'm aware with. Sorry, it might be something that the quantum research side of the company is working with. We have enough. We have enough work with the UK at this stage in terms of engineering. So yeah. Yeah.
And one that is interesting. How many years away do you think, with your expertise, is quantum computing from being used for commercial purposes?
I think so. It's like economical engineering question, both. It really depends on the investment. So if we keep and the amount of people, the talents that join the quantum community, in particular, I think engineers are a bit the missing link at this stage. Companies are really understanding that they need physicists to define the problem, but they need engineers to work with them. And there are, I can quote some other companies saying that they believe 10 years.
Okay.
I don't know how much they believe they will receive, they will be able to invest in that sense. And commercially, something commercially valuable can be something that is not really, that can still be done classically, but is like some as a form of learning and investment. So difficult to put a number. I wouldn't bet on that.
Okay. Would a QDC be useful? Quantum digital converter together with a DQC. I have no idea what that means, but I thought you may do.
I can probably try to. I would imagine that is the equivalent of an ADC and a DAC. I would say, just from the look of it. So something that converts from a quantum to digital domain and a digital to quantum domain. We basically have it. So we do have the conversion every time we need to actually use the results. So from I think the second one, the quantum digital converter. So every time we do a measurement, we need to take the block sphere, kind of freeze it, that the pointer will be closer to the North Pole or the South Pole, and what we call the state will collapse. We will basically get a 0 or a 1. We will run statistics of that. There are properties, but this is basically a converter. So you are moving from something that is similar to an analog signal that becomes a digital. The vice versa will probably be more complex, but it sounds like a loading of a quantum machine with digital data. I don't know if if it will be needed, but that it's just a matter of loading data into the system.
There's a question here. How does one see the output from the computation?
Does one see? As in, so
how do you visualize it? I assume do a computation, for example, of looking at your various biological samples. How would you visualize that?
That's something we working on, understanding how to. So obviously, what we are really at the basic building blocks here. So I can give you a number that is 4, but then obviously it's not something that will be as usable as giving you a graphical representation of that, matching that number to. We're still at the stage in which we basically get numbers out. Yeah. We don't have a full chain that goes back to a nice graphical interface. But we have done it for not quantum technologies. There are lots of companies that work. That's kind of the easiest part of the problem. So yeah, we can render the results on the cloud or on a website or.
Okay. Has any practical problem been solved by a quantum computer faster than the conventional one yet, or is it all still very theoretical?
So this is I can talk freely. I guess it's not something we have been involved with. There is the quantum supremacy problem that has been and there is a bit of like the community is a bit torn in that sense, if it's practical or not. So what's about is verifying that a random number has been generated by a quantum computer. And the interesting thing is that it kind of proves that the random number is not something that someone is sending to you. So the value of this is that I'm trying to simplify a lot of the problem. But what happens is that if with this experiment, if I receive a quantum number with this machine and I use the machine to verify it, I have a guarantee that no one has been sniffing my channel and sending me a random number that is not random. So if I send you one single number, you will always see it as random. But with this experiment that Google has run last year, they have a way to show you the number was generated with a quantum computer. So
okay. Time's getting on. We've got a few more questions. I'd like to ask my one. In fact, I'll take my privilege and ask you my question now. Yeah. I saw on the news today that IBM have announced that they have now produced in the lab some 2-nanometer devices. Mm-hmm. They will reduce power consumption by 75%. I've got a feel for quantum computers to whether the power levels it takes is comparable to a sort of a classical computer. The reason I ask this is the other data I saw was that computers now take more power than the world's lighting. So there is little sustainability issues, and just wondering if we're going into a high power domain.
Yeah. It depends on the acceleration we can get. So quantum computers are really hungry in terms of power, at least the existing one. So it's something like thousands of dollars to run 1 hour of for the cooling and all the properties. But if we think about problems like in transport or energy grids, or fertilizer, so they can easily compensate for the extra power that we need. Again, we are assuming that the technology keeps scaling up in this way and actually improves. Obviously, we know that on the classical semiconductors, we are approaching the limit of we are reaching the limit of the technology nodes that we can use. Power is now becoming even if the power consumption has dropped, economically is going to be more difficult to produce smaller chips. Few companies are still taping out only Apple, IBM, and few others are taping out below 7 nanometers. So, and this is always, economy is always driving these things, and we believe that quantum computers can play a different attack the problem from different side.
Okay. Bit of a technical question here. Does the collapse wave function reach a detector which is then translated into the numerical output?
reach a detector when so the collapse is caused by the measurement. So you have another way to see the block sphere is that you have probabilities of stuff, and this is a wave function. So I have a really high probability of being in the North Pole by kind of spinning around in that area. If I want to know if I'm in the North Pole, I do what's called a measurement. Measurement can be something that happens by nature and is by mistake, or we can drive it with in different ways. When we drive it, we use a detector, and this detector has already caused the collapse. Then we have readout logic on the detector that normally reads the number of photons that have been generated in the case of ion traps, or measures generates a frequency, runs an FFT on Fourier transform on the result, and gives us the 0 or 1. So the measurement is already collapsing. Is what we try to use? We try to continue from the collapse state to get more information after.
Okay. Is there an analogy between parallel and serial processing in quantum computing?
Everything is kind of so if you think about the music chart, everything on the same column is executed in parallel, happens at the same time, and everything that moves in the row, like as a music chart, is I would say serial. You can have quantum computers running in parallel. We still have, if we go like one notch up in terms of technology. Is the domain of quantum distributed networks, and it is quite appealing because if we reach a limit on the capacity of one, there are ways to create quantum computers, like virtual quantum computers with more systems connected and using complex ways to entangle them, but that's possible.
Okay. Just a quick look on the IBM website indicates that they're offering a quantum computing service accessed via a Python programming language. Are you familiar with this service, and what do you think this service is capable of?
So IBM is probably the best company in terms of the effort they're putting in educational and early access to the technology. I think they open access to everyone already a few years ago. They give you a system that they let you access a system that has limited number of qubits, but they are increasing the size. You have you pay different, obviously you have different costs for different technologies. Most of the programming language that are like the high-level programming language that I shown at the beginning, they are Python based, and this because what physicists want to do is they want to have Jupyter notebooks, so they want to have Python in a web browser, and they want to execute these complex computations, because the complexity is not in writing it, is actually in understanding how to write it. So the language they want a simple language because they already have enough problem, and IBM knows that, and that's why they are trying to simplify their languages.
Okay. The comment and the question. Quantum computers are currently room scale and analogous to mainframes of the 1970s. Are we likely one day to see embedded quantum computers in many places, or will they really only remain for special applications?
So we believe that they will remain for a bit. Now, with the current rate of technology, they will remain mainframes like for long. There might be breakthroughs. One could be new superconducting materials. There are groups working on room temperature superconducting materials. So the image I show with the massive pillar in the center, that's only for bringing the superconducting chip at 10 millikelvin. If you can operate at room temperature, it can be in a phone. And there are already, I was not aware, but my CEO told me last week that there are already some quantum inspired or driven chips that operate at room temperature. They can't do quantum computations, but there might be some quantum sensing, for example. There might be applications that will they will leave the lab and be in, maybe not in every mobile phone, but they will be on planes or on other technologies. So that's more the quantum sensing side of thing, but that's possible.
Okay. With quantum computing being so powerful, would it not cause a lot of security issues with things like banks? So in other words, I think they're thinking about early, very fast decryptions and people breaking into accounts, etc.
It depends on. I'm not familiar with the way that banks are encrypted. Banking system is protecting data. I know that the US, the same effort that has produced all the web security, the HTTPS and all the authentication, etc. The same, the NIST, the same organization, is already picking the best new quantum resilient post-quantum cryptography algorithms. What they do is they basically rely on computation that don't have any speed up in quantum computing. As I was saying at the beginning, the pyramid of things that can be made really fast on quantum computers is really narrow. The one we got so far, like the RSA and some authentication schemes, are really vulnerable to existing quantum computers, in a sense that quantum computers can really solve those problems fast.
Okay.
It doesn't apply to others. So elliptical curves are immune, others are.
Okay. Which nation is leading the way in quantum computing in terms of investment and R&D? What about progress in China? And is there any collaboration with the Chinese, or would Mr. Trump have sort of banned them talking about quantum computing?
So I think in terms of investment, the US is leading. Okay. I don't know if it's leading in terms of private investment or private and public investment. UK is doing quite well. Europe is same. Every country and continent I can think of has some efforts going. It's really difficult to see in terms of like versus GDP or numbers, which one is investing more. China is investing. They've done a counter experiment to the Google supremacy one, and with extremely successful one. So yeah, there are two sides of things. I would say there is the pure investment and how the investment is, if the investment is focused or not, or if it's spread across multiple technologies. So yeah, I would say that probably, yeah, the US is driving the investment. I don't know, I would probably the R&D as well. Yeah. There are lots of second places.
Okay. And finally, the last question I have is, where does Schroedinger cat come into the talk? In other words, how does that connect to quantum computing?
Oh, okay. So yeah, it is a bit of a stretch on the.
It's a nice looking cat though.
Yes, in a box. So I think it started as an internal joke in the company that we had a lovely Schroedinger cake for Halloween, and now we keep using it internally as a joke. Schroedinger will be more for quantum physics and quantum computation, but still, I think it's nice to have a nice picture at the beginning.
And thank you very much indeed, Marco.
Oh, pleasure.
Indeed. Thank you, David. Marco, it's only through the generosity of speakers like yourself and the companies that you work for that we're able to put on these events. And it was really interesting to hear your insight into the field, and to hear where Riverlane are going in the direction of research and development. So thank you very much. Okay, well, that brings us to the end of tonight's event. I hope everyone enjoyed it and found that interesting. Please keep an eye out for our future events, and you can find those if you search for the IET Cambridge community website. And don't forget to register in advance to make sure you get a place. So on behalf of the IET Cambridge Network, I will thank you for joining and let you log off now. Thank you very much.